Well, I would say without him there would be no automotive Ethernet. So thank you, Thomas, for making all this possible. And the presentation is called Analysis of a Low-Cost Gigabit Diagnostic Interface. And I think a lot of it started with diagnostic interface. This is a nice circle to come back to now at this time. So welcome, Thomas, and we're looking forward to your presentation.
So hello, everybody. So I'm the last. Hopefully you do not fall to sleep with 2 long days. Thank you, Kirsten, for the introduction. So it's really like this. Sometimes I have the feeling that the future is a little bit circular. So a lot of the things that I will show you today was one of the primary leading thoughts for the first implementation. So just want to give you some background information. So as Kirsten said, in the year, and it's really now 17 years ago, there was the request to have a software update on a car, and the solution space that we had in the year 2004 was a bunch of technologies. Most, because this was the multimedia system we had, USB, Firewire, Ethernet, etc. So there were a lot of options. How could we plug a car? So then we decided for Ethernet, and we decided for 100-base TX because of some benefits. There was no DC coupling. Every PC single set has an Ethernet connection. It is a very cheap and robust interface. We can use a standard OBD connector. We'll show you them some examples for it. And there are effective software stacks available. Yeah? And we can say only with the decision having this there, it was possible to make a software update of a car in the field of 15 minutes to half an hour. If we would not implement this interface, we would need, let's say, 16 hours and more. So what I want to show you now and discuss it with you, or explore it with you, are the thoughts that leads to this type of solution. So the question that we raise is why it is possible to use a non-standard conform solution with 100-base TX with enormous efficiency for the diagnostic use case and for the program use cases. And that is a question, why it is working. So the thing is that we said we need a clear analysis of the use case where we need it and how we need it, and we need a clever combination. And by having this combination with a clever idea behind, it was possible to come to this conclusion. So when we said use of a standard diagnostic connector, it means we have to make compromises. So this connector is never ever a high-speed, perfect connector. It is not perfect, but the message is it's good enough. But the thing is we have to make compromises. And you have 2 options. Whether you say we need a perfect connector, maybe you wait some years for it, or will never be there, or you try to make a compromise and have a good combination all of it. But to understand what compromises you can make without killing yourself, it is very important to understand the essentials of EMC requirements. And it's important that you have to understand the diagnostic system not as a connector or an interface. You have to look to the whole chain, to the whole system. But first of all, I want to look to the diagnostic connector. What does this mean? And this is very essential. So in the diagnostic connector, there are some pins marked here in blue. These are the pins that are OEM specific. So the rest marked in black is standard conform. It has to be standard conform. The blue ones can be decided by any OEM what kind of features they want to put on. And in the year 2006 or 7, I don't know the details anymore, I decided to use 4 of them and using these 4 pins for 100-base TX. Another vendor, another OEM comes later and they have a problem that these pins are not perfectly fitting for them because they have some features on, so they have 2 pins as a different one. And these 2 options are now known as a DOIP interface for the vehicle access. Nobody asks the question why this is not standard. It's there. An important thing is that there on this connector there are 2 pins. They're important. One pin is the power supply of the car, ground of course, and the other pin is an activation line. So when we talk about understanding the EMC requirements with two things, the EMC emissions and the EMC immunities, and the EMC immunity. In this use case of diagnostic, we have two use cases. A use case where the car is on the road and there is no diagnostic done, and another use case where the car is in a standard use but with diagnostic on. In a situation where their car is on a standard, let's say a customer use case where there's no diagnostic available or needed, we detect this by looking to the activation pin. If the activation pin on the OBD connector is off, so that means there is no diagnostic system connected to the system, the gateway detects it and switches off the Ethernet line. So that means there is no EMC impact on any of the system because the diagnostic PHY is switched off. In the other situation where the system is activated, the activation pin is on, and in that case there is an EMC effect on the cable between the gateway to the diagnostic interface. But you should not forget, in the same time, you plug a PC on the system. It's not only the interface that's on. So that means in this diagnostic use case, there is an EMC issue seen on the interface, but it doesn't matter because the PC has minimum the same level of noise that is covered. For the immunity way, the other way around, so that means there is noise coming to the car, and the question is, okay, how do we overcome this immunity? The same message. Car in the standard use case on the road, diagnostic interface switched off, no impact as there would be no PHY connected to the system. And while the other use case, while the car is in a diagnostic mode, there is still the requirement of having not a safety critical malfunction, but this is standard. So this is a standard feature of the system. And again, I have a lot of discussions today where somebody tells me it's a safety relevant bus system. I'm not sure that this is right. So a communication system can always fail, but that does not mean that it causes a safety functional critical malfunction. This is a big difference here. So when we now look for the onboard diagnostic connector, this cheap connector and 1000 base T1, I'm just talking about now about the options. First, before we go to the 1000 base T1 use case, we still look to the today's state-of-the-art 100 megabit solution here. What you see, and that's important to understand the big picture here, on the left side, you see the diagnostic gateway with two twisted pair of cable directly connected to this diagnostic interface, the OBD connector, inside the car. Then you have a cable that's connected with two pairs, one RX direction, one TX direction for 100 base TX, an activation line and the power supply of the car. On the other side, you connect a PC with a special connector where this activation line is decoupled to the system, and the rest is still a RG45 connection to a PC. On the test application is normally a standard PC, whereas a standard PHY or switch used in a PC, where this normally is in a multiple mode for 100 base TX and 1000 base T. AutoNEC normally is the basic to decide what kind of speed grid you're using. Now when we talk about gigabit, and that's important to understand, we do a very similar thing. We say, from the left side, we now talk about the gateway, where there's only one twisted pair connection to the diagnostic interface. There is a one pair with full duplex based on the 1000 base T1 standard to a media converter outside of the car. This media converter has the job to transport or to convert 1000 base T data to 1000 base T1 data. So it's a media converter, as you already know. On the other side, on the PC side, on the tester side, nothing is changing. It's the same. This is the idea how we would deal with a gigabit interface, a very cheap one in the car. So now we look to the pin that we could use for this too. Again, we don't need 4 pins, we only need 2 pins. And I just decided to use the pin 12 and the pin 13 because it's the same of the both actual solutions that are available today. and connecting this to a 1000 base T1 PHY in the car. This looks very easy. When we look to what does this mean for a situation today, for car fleets or for the solution that we are looking for, you see that they have whether the 100 base TX solution already shipped today, millions of cars, or you go to a 1000 base T1 solution down, and in the middle you need an intelligent adapter or a diagnostic adapter that deals with this information and transport the communication due to the features of a media converter. So if you look now for a cost comparison, you see that if you go to a 1000 base T1 PHY, the in-vehicle costs are very similar to today's situation. So there's really not a big cost adder. Why? The PHY, normally integrated in a modern switch today, is identical. Normally you can switch the modes of the switch between a gigabit and a 100 megabit mode, and you just use the PHY and switch it inside the switch. You switch it to a gigabit mode instead of a 100 megabit mode. The rest of the BOM is the same. From a cable point of view, we can make a cost down, 2 twisted pair cable to 1 twisted pair of cable, and the rest of the BOM is really comparable. The only thing what you need is outside of the car, you need a media converter. But the good news is this media converter is not needed per car, it is needed per diagnostic station, yeah, and not per car. So there is no additional cost adder for the car. So if you again look for future car fleets, because we all have to talk about always a migration phase. You build a car with the old interface, with the new interface. Maybe you come at the dealership, you meet 2 cars with the old interface, with the new interface. And one of the ideas is to build this external combo interface, where this external combo interface has some intelligence to just try to build up a connection with the old one. If it's not working, it's switched automatically to the new one. The rest of the diagnostic system, mainly the test application, does not see any of the change of the internal interfaces. So this gives a very good flexibility and leads to, let's say, a way to do a migration to the new system. So now I want to give you some results and the conclusions that we have when we do now the test of the system here. So if you were in our booth, you see this demo setup, and this demo setup is very interesting because you see 2 media converters. So one media converter near to the OBD connector on the top of this box is representing this media converter outside of the car. Down the line, the other media converter is representing a gateway that gets the data via this, let's say, very cheap connector and a standard twisted pair of cable. Inside our media converters, we have traffic generators that generates 1 gigabit traffic full duplex in both directions. And there is a monitoring tool where it can be connected optical to do some EMC tests, of course, but you can see it directly on your desk. And you can see the data throughput, you can see the packets, and you can even see if there's any CSC error. Yeah? The messages, the data communication is very robust, the SKA value is excellent, and the bit error rate, as expected, has to be down to 10-14. So the messages, if you would rent this modular system, you can use it, I can give it to you. If you find a bit error or CSC error, I pay you a beer. So I just see that there is a problem with the scripting. Sorry for that. What you see here is the results on the EMC in a nutshell. In a nutshell means I try to eliminate the limits as a detail to give you an overview. When I'm talking about the system, I do not talk about on the diagnostic interface. I have to talk about the diagnostic system. What you see here are, let's say, different levels. You see 2 things. First of all, the EMC emission stuff and the EMC immunity area. What you see is the limit in automotive based on the UN ECR R10, so it's a car specification for it. Then they're based on the CISPA 2025, it's due to emissions, and the ISO 11452 based on the immunity requirements for a car. What you see there is the performance of the interface itself. in, let's say, a little bit more abstract, not in detail limits, I would say from the emission point of view, we can come close to the limit of maybe even if it's activated while system is on, maybe with an acceptable reception. The immunity is good enough for the interface only. But if you look to the CE requirements that you have on the PC side of the tester equipment that is connected while the diagnostic interface is done, this are much, let's say, higher limits. So that means the diagnostic interface itself is better than the rest of the system. So that means this diagnostic interface, interface is good enough to have the basic for the system there. So the messages, EMC certification for the diagnostic system based on the CE standardization is possible, and the bit error rate is very, very low, and the system is robust enough to do not have any big issues in the field. So as a conclusion, so I'm really quick, hopefully. So as a conclusion, the multi-gigabit networks, because we have more than 1 gigabit link inside a car, for my opinion, need a high-performance diagnostic interface. 100 megabit is really now not good enough anymore for this multi-gigabit networks. 1000 base T1 will work over a standard OBD interface. The EMC issues are under control, and the availability and the robustness of this interface is really good. If I compare it to the 100 base T1, to the 100 base TX interface, I would see even better than the old one we have. It's always in the field. We have cost savings or minimum the same cost compared to the 100 base TX solution. And first test ups, as you see, are already existing, and that's why I'm pretty sure it is a way to go forward. Thank you.
Thank you, Thomas. Okay, I think we have the first question from Haysam.
Yes. So this discussion came up in J1962. And
could you say what J962 is?
So SAE J1962 is an SAE specification in the US for OBD2 connector. Mm-hmm. And on that connector, they have the CAN FD channels, and they have 100 base TX. So they want to add 1000, and now they're considering an option to add 1000 base T. We suggested T1, but the committee is, the idea is you always have to be backwards compatible. Have you took this proposal to them? What did you suggest this to the SAE committee at all, or?
No. No, I didn't. The question is, what do they mean with backwards compatibility?
But basically, in an OBD connector, nothing can be removed. So if K-line is on there, or UART or CAN, it has to stay on there because it has to work on all vehicles tracking back to the early 1990s. Right. So right now, there's not that many pins left to add base T. And I raised concern saying you cannot just pick any pins. So there's 2 pins available. I saw the 2 pins you showed. But they don't want to implement T1. But I think it would be good to take this to them to show them that if we implement T1, it's possible with the media converters.
Yeah, right. Maybe some answer for that question. So the thing is, when we decided for DOIP... When we decided for DOIP or for Ethernet as an interface, we use OEM-specific areas. And as far as I know, even especially in the US, on the CARB, they do not accept DOIP, they use CAN-FD for the regulation. So the message is, what we can do is we can say from the 4 pins that is used for OBD, we use 2 pins for the 1000 base T1 standard, so for the 1000 base T1 interface. That does not mean that they kill an old interface. That only means when you have a new car, it will be diagnostics via 1000 base T1. If an old one, it will be done by 100 megabit with the same functionality, with the same features. Maybe that is a compromise for them to show them the future.
Yeah, so the idea was I suggested why not investigate base TX, because you can use the 4 pins as 100, but that's not common in laptops. So the question is for them, how can they just use a laptop to connect to the vehicle?
Yeah,
so
the message is use a media converter outside of the car, It's supplied by the power supply of the OBD connection, so there is no impact. So you connect the connector. In the connector, the media converter is directly placed outside the car, part of the diagnostic system, and job is done.
So I think what we need to do is we'll get offline, me and you, and we should take this as a proposal because we're working on this now. So if you have something, then we should work on it.
You're welcome.
Okay.
Entschuldigung, sorry.
I think Jamila has a question.
But you seem to have some online as well.
I have one online right now.
Okay.
There was on
No,
one of the
actually
slides.
not Harry.
We're good in time.
Jamila, go ahead.
On one of the slides, you addressed that there is an expectation of improved BOM. Could you clarify that? Because I think maybe there are some aspects which were not considered. For example, the hardware bootstrapping at the hardware level, when you are shifting between the two, so to say, communication.
Okay, so the communication is whether a 100 base TX or a gigabit interface. The trick switching between is to try. It's a try and error system where let's say the combination interface from the outside is first trying to build up a link on the 100 base TX system. If it's failing, it's switching on to the rest of the system. There is no bootstrapping inside the system. Okay,
So it's expected that you can shift to the diagnostic mode even without having that implemented at the hardware level. Is my understanding correct?
No, you don't. What you have is you have the activation line, and if the activation line is on from the outside world, it is clear, it is a must that the gateway has to switch on this link. It doesn't matter what kind of functional implementation is on the back. So that means if the, let's say, intelligent adapter from the outside world sees activation activity, he knows that after some 100, 200 milliseconds, he has to expect a link to the car. That's why he tries first 100 base TX. If the link is up, everything okay, then he's passing forward. If there is no link up, he's switching to the 1000 base T1 mode automatically.
Okay, and the point that this leads to BOM reduction, what's the exact connection there?
The situation is the following one. Today, in a new design, as you know, the PHYs that are already implemented in the switch can play more roles. 1000 base T1 or 100 base T1 mode. There are special ports that can deal with 100 base TX, but it's not very, let's say, friendly, but it's not good. It's a different design. And today, it leads to a situation that a switch can play different modes on the PHY ports. And the message is why it's, let's say, BOM transparent, is to say I have the same interface as it would be a 100 megabit interface, but I only switch the PHY to a gigabit mode, and that's the result here.
Okay, I can politely agree to disagree because I think then to use the term BOM, we would have to include different components within the implementation to really say that this leads to such a reduction.
So it's not, let's say the BOM reduction more or less is I use one cable instead of two, the rest should be the same. So the bill of material means you only have one line instead of two lines inside the car from the diagnostic connector to your connector.
Okay, so you mean then at the implementation, but not really actual component as it is, right? If I understand you correct.
Yeah, one line instead of two pairs. So one pair instead of two pair is a reduction.
Okay, thank you for that. I have only one contribution in regards to what Haysam was asking before. And my understanding is basically this media converter setup. You can even consider that you have on the other side a camera sensor. So do you still see this connection proposal as something new? Because typically, let's say if we were to check any camera sensor applications, normally we would have such a setup. So for me, that's why I was wondering.
So the thing, if you would ask me the question 15 years ago, I have to say, sorry, it's only CAN FD, it's only CAN on this connector. 15 years ago, we at BMW decided to have 100 megabit on the connector. And now it's an option to say, why not go to gigabit on this connector with the same strategy, with the same basics as 15 years ago. And I think the 100 megabit interface was very successful because I've never any EMC issues or any EMC problem with this interface. So the question is, that's why I said I do not make any proposal to the industry. I just want to show you in this conference room here that there is an option to do it. If I would be you, I would try to do it.
Understand. So the emphasis, yeah, you're trying to set an emphasis on the fact to sort of say to shift into higher data rates, but the setup as it is, it's something that has been already deployed, right?
So the design today, if you design a new system or a new car today, I would think with the new files, with the new switches integrated in this system, would be relatively easy to do it. And a media converter is not a magic thing.
Okay, thank you.
Okay.
Okay, we have one question from Christoph Gollop. And my phone is behaving weirdly here. When we put a 1 gigabit link onto a predominantly 100 megabit IVN, wouldn't there be a risk of actually losing packets in the gateway to the vehicle because we're overloading if we do not coordinate the flash sequence correctly? And I'm paraphrasing because it's always scrolling away, so I can't read it off really.
I understand Christoph's question. I think it's the problem of mixing of speed grades. So if you start to go to a car with a high-speed interface and you do not take care what's happening inside the car, you can up to a situation where you overflow the input. But this is a problem that is always there if you start to mix speed grades. There exist different options to overcome this problem, but you have now two options. Whether you say you go to a low-speed interface because you are afraid of mixing speed grades, that's one option, and then you can do it. The other way is you can say, I go to a gigabit interface and try to activate methods to prevent speed grade mix. It's not a good idea to only believe on TCP will help you. So in that case, we need some configurations to deal with the mix of speed grades.
Mm-hmm. Okay, I think that's one of the topics we discussed yesterday too, just for that reason as well. No more questions? No more questions on the line either. Then I'd like to thank you, Thomas, once more for the presentation and for making the loop back to the beginning. So thank you very much.
Thank you.